Okay, next we are going to learn the formal proof, which is a proof by induction of de Moivre's theorem. Okay. Now, we have to know this for all natural numbers. So it is a formal proof on the course. Okay, so make sure you're trying to understand it line by line as I go through it. So we're going to start off, right? What is it that we're actually trying to prove? So first of all, de Moivre's theorem is r times cos theta plus I sin theta, all to the power, so keep it all in a square bracket to the power of n. That is de Moivre's theorem. Should equal r to the power of n by the cos of n times the angle plus I sin n times the angle. Okay, so that's de Moivre's theorem. You bring down the power and put it on the modulus, r, and then you're also multiplying the angles by whatever the power is as well. So that's de Moivre's theorem. Okay, so step one for induction, proof by induction, you show it's true for n equal to 1. Okay, so prove true for n equal to 1. So your left-hand side, so remember this is your left-hand side, if you could do it all in the one go, that's perfect. So it's going to be r, a bracket, cos theta plus I sin theta, and it's all to the power of 1. That would then read as r to the power of 1 by cos times 1 theta plus I sin 1 theta. So therefore your left-hand side is equivalent to your right-hand side straight away, because anything to the power of 1 is itself. So your left-hand side works out to be r cos theta plus I sin theta. The right-hand side works out to be r cos theta plus I sin theta. So therefore it's true for n equal to 1. Step 2. Given that the theorem is true for n equal to k, so if it's true for n equal to k, what that just means is that r times the cos of theta plus I sin theta all to the power of k is equal to r to the power of k by cos k theta plus I sin k theta. So I'm assuming it's true for n equal to k. Okay, next I want to prove, so what is it I'm trying to prove? I am trying to prove it's true for n equal to k plus 1. Okay, so such that my left-hand side is r a bracket cos theta plus I sin theta, and the whole thing is in a bracket, all to the power of k plus 1. And using de Moivre's theorem, that would be r to the power of k plus 1 by the cos of k plus 1 times theta plus I sin k plus 1 times theta. So that's what I'm trying to prove. So put that in a box and highlight it. Okay. Now, we're going to work with our left-hand side of the proof. So I suppose this would be easier if we could do it all in the one go and you could actually fit it across the page. So I'm going to try and actually do that. Okay, so r cos theta plus I sin theta, sorry, square bracket, that's to the power of k plus 1. Okay, and that is equal to my right-hand side, which is going to be r to the power of k plus 1 times cos k plus 1 times theta plus I sin k plus 1 times theta. Okay, right, so I basically want to show that that will end up looking like that. Okay, so what I'm going to do here is I'm going to apply my rule of indices. Right, so this is already applying de Moivre's theorem, so there's no point in applying de Moivre's theorem to the left-hand side as well. I've already done it to the right-hand side. So I'm going to use rules of indices. You would add the powers when you would have multiplied the base numbers. Okay, so this can now be split up. Okay, or cos theta plus I sin theta to the power of k multiplied by or cos theta plus I sin theta, and that will be to the power of 1. Okay, so that is all to the power of k plus 1 when you'd work it out. Now, from this part here, I am going to apply de Moivre's theorem. Okay, so bring down the power in front. Alright, sorry, there should be a bracket around that. The same way that it should be a bracket. There, yeah. Okay, so I'm going to bring the power of k down, so it's going to be r to the power of k times cos k theta plus I sin k theta. Okay, so that's that. And it's still being multiplied by this square bracket. So multiplied by, or, and again, there should have been brackets around those, or cos theta plus I sin theta. Okay, and that's still all equal to that right-hand side there. You can keep bringing down the right-hand side. Okay. Now, these are being multiplied together. So again, remember I am going to use my knowledge here of if I multiply, or they're all multiplied together, right? Those four brackets. So it doesn't matter what order you multiply them in. So I'm just going to put the two r's together. So I've got r to the power of k multiplied by r. Okay, then I have cos k theta plus I sine k theta multiplied by cos theta plus I sine theta. Okay. So rules of indices then. Wouldn't you add the powers? So that's an r to the power of 1. So I'll add those powers and I'll get r to the power of k plus 1, a bracket. Now, I am multiplying these. So what you can do here is multiply it all out. The fact that they are in polar form, technically what you should be able to do, but because of this proof you actually can't use this method, but normally you'd say, right, well I would say this would be cos, in a bracket, k theta plus I sine k theta plus theta, and that would be coming from our multiplication of complex numbers when they're in polar format. However, because this proof is a proof by induction, we have to go a further method. We have to pretend as if we didn't know that was a rule for multiplying complex numbers, and we have to go with the longer method, which is actually splitting the brackets and multiplying it all out. Okay, which is what I said in a previous example not to do because it's so much more cumbersome and time consuming, but it still gets you your answer. So unfortunately we have to do it this way for the proof. Okay, so what I am doing is I am splitting those two brackets and multiplying them out. Okay, so it's going to be the cos of k theta multiplied by the second bracket, cos theta plus I sine theta, okay, plus I sine k theta multiplied by the second bracket, which is cos theta plus I sine theta. Okay, remember all of this should be equal to that right hand side there. That's what I'm trying to get it to look like. Okay, right, close that outer bracket. Now I'm going to multiply all this out. So I've got r to the power of k plus 1. Okay, cos k theta multiplied by cos theta is just cos k theta cos theta. Cos k theta multiplied by I sine theta is just going to be plus I cos k theta sine theta. I sine k theta by cos theta is plus I sine k theta cos theta. And then I sine k theta multiplied by I sine theta. Remember, I by I is I squared. Sine k theta sine theta. And again, all of that should equal that right hand side from up there. Alright. Okay, so let's start tidying things up. Now, group your real parts together and group your imaginary parts together from this. Okay, so if I just remember now, this is minus 1. I squared is minus 1. So if I just even scribble that in on top of that, that's going to end up being minus 1 times sine k theta sine theta. So the I is gone from that. So if I group my real parts together, anything that doesn't have an I in it, right, that's real. That is imaginary, that's imaginary, and now all of this is real. So they're my two real parts and they're my two imaginary parts. So I'm just going to rearrange it. Okay, so rewriting that and multiplying it out. Or to the power of k plus 1, a bracket. Minus sine k theta sine theta. So that's all my real part, and then the imaginary part is these two terms. So if I actually factor I out straight away, so plus I a bracket, I'm going to get cos k theta sine theta plus sine k theta cos theta. Okay. Now, again, let's look at what it is I'm trying to get this looking like. I want that to look like this right-hand side. So I have the r to the power of k plus 1. Right, I have that already. I need to try and get it looking like this. Now, so I have an individual cos of an angle plus I sine of an angle. But if you look down here, what have I got? I've got cos by cos, sine by sine, and the same over here. So these are products. So you're going to have to use your knowledge of turning products into sums, sums into products, or any other trig identities from page 14 or 15 of your log tables. So if you can find a formula that looks something like this, where you have cos of an angle, minus sine of an angle, sine of an angle. Now look, that angle is k theta and that's k theta. So if you call that angle A, right? So like if I put an A over that, and if you call that one B, well, this is A as well, and that's B. So you're looking for a formula that has cos A, cos B, minus sine A, sine B, right? In your log tables, you will find the formula for cos of A plus B, right? That is the formula that you're going to find. So A is k theta and B is theta on its own. So in using that formula, I now know that this real part of my complex number can now be written as the cos of A plus B. Okay, so it's going to be r to the power of k plus 1, bracket. All of this, so all of that, is now going to be written as the cos of A plus B. Well, A is k theta and B is theta. Okay? And again, if you look at this side, same thing again. Look, that's A, that's B, that's A, that's B. So you are looking for a formula that has the cos of A sine B plus sine A cos B. Right? So you look in your log tables and find a formula that looks like that. And you'll see that you're going to use the sine of A plus B formula, because sine A plus B is equal to sine A cos B plus cos A sine B. Alright? So, this is now going to be plus I times the sine of A plus B. So A is k theta, B is theta. Okay, so slowly but surely we're getting there, right? So remember, I'm still working with the left-hand side. I want to get it looking like that right-hand side. The only difference between the left and the right-hand side now is the angles. So this angle is k theta plus theta, whereas up here, it's k plus 1 by theta. That just means I obviously factored out theta from both. So factor out a theta from both of those. Okay, you can see it's common to both. So you are going to get r to the power of k plus 1, a bracket, the cos of, if you factor out a theta, I'll put it on the right hand side of the bracket. I factored out theta and you're going to be left with k plus 1 inside the bracket, and it's the same over here, I sine. Factor out a theta and you're left with k plus 1 inside the bracket. Okay? So you have now gotten your left hand side to look like that right hand side the whole way down. Okay? So do keep constantly bring down that right hand side, just to show that you are eventually getting it to the way you want it to look like. Okay? Last step then, don't forget your conclusion. So you showed it was true for n equal to 1. You assumed it was true for n equal to k. You have now proven that it is true for n equal to k plus 1. Okay, so your conclusion, make sure you have it. So therefore, by induction, de Moivre's theorem is true for all n is an element of the natural numbers, because we already proved it's true for n equal to 1. We proved it was true, or assumed it was true for n equal to k. Therefore, by induction, it is true for n equal to k plus 1 for all n is an element of the natural numbers. Okay, so that is your proof by induction of de Moivre's theorem for natural numbers.